Hey there, and welcome. Today, we're jumping into one of the most practical and I think coolest applications of calculus, something called related rates. It's a powerful way to see how all these different moving parts in the world are actually mathematically tied together. So let's kick things off with a simple question.
So imagine you're blowing up a balloon. The air is going in at a nice constant rate, let's say 100 cubic centimeters every second. The balloon's volume is growing steadily for sure. But here's the real question. Is the radius of the balloon also growing at a steady, constant pace? It's a great question, and your gut feeling might tell you one thing, but calculus lets us find the precise answer. So let's grab the numbers from a classic textbook problem and see what's really going on.
Okay, so here's the setup. We're given the rate of change for the volume, what we'd call dV dt, and it's a solid 100 cubic centimeters per second. The unknown, the thing we want to find, is the rate of change for the radius, or dr dt. And we're not looking for it the whole time, just at one very specific moment, the instant the diameter hits 50 centimeters.
And this gets to the absolute heart of the matter. Even though the volume is increasing steadily, the radius is not growing at a constant speed. In fact, as the balloon gets bigger, its radius actually starts to grow more slowly. Their speeds are connected, they're related, but they are definitely not the same.
And this whole idea has a name, of course: related rates. It's the tool we use for exactly this kind of problem. It's what lets us take a rate we can easily measure, like how fast an air pump is working, and use it to figure out a rate that's much, much harder to see directly, like how fast the radius is changing at any given second.
All right, so that's the big idea. But how do we actually do it? What are the mechanics? Well, the best part is you don't have to reinvent the wheel every single time. There's a step-by-step game plan that we can follow for pretty much any related rates problem.
And here it is, the 7-step strategy. First, you just read the problem and try to sketch it out. Then, you give everything names, variables for all the things that are changing over time. You identify the rates you know and the one you're hunting for. Now, the real core of it is step 5, finding an equation that connects all your variables. Then, the magic calculus step. You differentiate that whole equation with respect to time. And finally, you just plug in all the numbers you know and solve for the one you don't.
Okay, enough theory. Let's get our hands dirty and actually see this strategy in action. We're going to use another classic famous example that really makes these 7 steps click: the sliding ladder problem.
So get this picture in your head. There's a 10-foot ladder leaning against a big vertical wall. But, the bottom starts sliding away from the wall, moving horizontally at a steady speed of 4 feet per second. Now, if the bottom is sliding out, the top has to be sliding down, right? So the question we have to answer is this: exactly how fast is the top of that ladder sliding down the wall at that one specific moment when the bottom is 6 feet away from it? All right, time to follow our own rules. Let's set up some variables. We'll call the distance on the ground x and the height on the wall y. The problem gives us dx over dt. That's the speed of the bottom sliding away. And what we need to find is dy over dt, the speed of the top sliding down. Okay, on to step 5. We need to find the bridge, that one equation that links x and y together. We'll look at the picture. The ladder, the wall, and the ground. What do they form? A right triangle, which means we can use our old friend, the Pythagorean theorem. And there you have it. X squared plus y squared always equals the ladder's length squared, which is 10 squared, or 100. This is our master equation. It's the relationship that's always true, no matter how much the ladder has slipped. And now for the main event, the big calculus step. We're going to differentiate both sides of our equation with respect to time. This is how we go from a static snapshot of positions to a dynamic movie of speeds. Using the chain rule here is what's going to bring our rates, dx dt and dy dt, into the game. And voila! This is what we get. The derivative of x squared becomes 2x times dx over dt. The derivative of y squared becomes 2y times dy over dt. And of course, the derivative of a constant like 100 is just 0. So now, finally, we have an equation that actually relates the speeds themselves. All right, we're on the home stretch. We just plug in everything we know. The problem asks about the moment when x equals 6. We can use our original Pythagorean equation to figure out that when x is 6, y has to be 8. We were given that dx dt is 4, so we plug all that in, solve for dy dt, and we get -3 feet per second. Now, don't ignore that negative sign. It's super important. It tells us that the distance y is decreasing. In other words, the top of the ladder is sliding down the wall. Okay, so we've conquered balloons and we've conquered ladders. That's cool and all, but what's the big deal? Why is this such a fundamental concept in calculus and really in science? Let's zoom out a bit. It all comes back to this one single powerful idea. The derivative isn't just some abstract formula you memorize for a test. It literally means the instantaneous rate of change. It's the mathematical language we use to describe a world that is constantly in motion. And once you start thinking in terms of rates of change, you see this concept pop up everywhere. In physics, you're talking about velocity and power. In chemistry, it's the rate of a chemical reaction. Biologists use it to model how quickly a bacteria colony grows. Economists use it to figure out things like marginal cost. You can even use it in sociology to model how fast a rumor spreads. And really, this quote from the source material just ties it all together perfectly. All of these different ideas from all these different fields, they're all just special cases of this one powerful mathematical concept, the derivative.
So, I'll leave you with a final thought. Now that you have this new framework, this new way of thinking about how a change in one thing is connected to a change in another, start looking around. What connections can you spot? From the water level in a draining bathtub to the changing shadow of a flagpole, what related rates are shaping the world around you? Thanks for watching.